Okay, so second informal astro seminar of the semester. We have Ho-Yeuk Cheung, gravitational-wave astrophysicist. Marked his undergrad in Hong Kong, then moved to Johns Hopkins, and he worked on numerous topics in gravitational-wave physics and data analysis during his PhD. And so today he'll tell us about testing GR and astrophysics with gravitational waves.
Yeah, thank you very much. I'm Mark, I'm a new member here. So today I'm going to talk about some of the things that I've been doing in my PhD. So I'll be reusing some of the slides from my defense. But then I'll also talk about some of my ongoing projects and also some things that I want to do at the institute. So if you want to collaborate, then pay attention. So, okay, so I bet all of you know what gravitational waves are. See whether this behaves.
I'm gonna click on the slide.
Cool. Yeah, great.
Should
Okay, good, yeah. Okay, so I bet all of you know what gravitational waves are, but intuitively, I try to understand it like this, right? So let's say we have space-time, right? And then we put a bunch of test particles like a ring like this. So if this is static space-time, then nothing happens, right? But what if we put two black holes, one to the right, one to the left, right? What would happen, right? This would happen. It gets stretched in one direction, squeezed in one direction, right? The test particles. So what if the two black holes are rotating against each other, right? They're spiraling. Then the test particles would also, like the polarization of this stretching and squeezing would also rotate, right? Now, space-time doesn't only exist on this plane, right? It also exists here, it also exists here, right? So this stretching and squeezing, this rotation will propagate outwards, right? And these are what we call gravitational waves. And as you can see, if the binary is rotating like this, then the gravitational waves will be circularly polarized. And if the binary black hole is rotating like this, then the stretching and squeezing would be what we call plus polarized, right? Because it's like, the polarization is not rotating, it's just stretching and squeezing, right? So these are gravitational waves. And when they hit the Earth, we can detect them with gravitational wave detectors like LIGO, Virgo, Cagra, and I bet you went to Salvatore Vitali's talk on Tuesday, and he gave a very good explanation of what gravitational waves are and how we already detected many gravitational waves, right? So these gravitational waves, at the very beginning, the frequency is pretty low, and then the frequency goes higher and higher, and also the amplitude goes higher and higher because the two black holes, they are getting closer and closer to each other because they lose energy by gravitational waves. And in the end, they touch, they merge, and finally they settle down into one final remnant black hole, right? And so these are very exciting times. So I think Salvo also showed this plot in his talk. We are currently in 2025, right? So we are like almost at the end of this 04 observing run, but all of the things that Salvo talked about, most of the things that he talked about only comes from this small stretch of the observing run, so 04A, right? But there's also 04B and 04C, and this data is yet to be released, so there are many exciting things that we could potentially see. So for the outline of my talk, in the first part, I'll talk about how we can test general relativity with gravitational waves, specifically by using the ringdown stage of binary black hole merger. And in the second part, I will talk about how we can inform astrophysics with gravitational wave detections. Okay, and specifically, I'll talk about gravitational wave lensing. I'll show some exciting preliminary results, and also some search for high mass ratio mergers, which I've been doing with Matthias and other people at the IAS. Okay, so for the first part, testing GR with the black hole ringdown. So gravitational wave looks like this, and we can more or less divide this into three stages. We call the first stage the in-spiral phase, where the two black holes are pretty far away from each other. They're just like spiraling against each other. And then when they touch, it's the merger phase. And in the end, when it wants to settle back down into a stationary curved black hole, it will ring away gravitational waves in this stage that we call the ring down stage. And this is the stage that I specialize in during my PhD. So how can we compute the gravitational waves that are emitted during this stage? Well, we can use black hole perturbation theory because we know that the space-time will just be background per space-time, and then on top of it, there will be some small perturbations. Then we can try to solve for these perturbations by linearizing the Einstein field equations on top of a curved background. And the equations, like schematically, it looks like this. This is called the Tukhowsky equation, and it's just a complicated version of the Schrodinger equation, like outside of a hydrogen atom. It has the same structure. It is separable, and it can be solved. So after you separate this equation, then you will have to impose some boundary conditions in order to solve for the waves. And the boundary conditions are pretty easy to understand, right? At the horizon of the black hole, everything has to go in, right? And at infinity, we're not shooting anything inside of the black hole. So at infinity, everything has to go out, right? And after you apply these boundary conditions, you'll find that the gravitational waves, they have to follow this form. It's just some a times e to the I omega t, right? And there will be a lot of discrete so-called quasinormal mode frequencies that are allowed. So just like a hydrogen atom. And we label them with mode numbers, right? Just like the quantum numbers. So Lm is like the spherical harmonic number. And then n labels the different modes inside of one spherical harmonic. Okay. And these omegas, they are complex, right? Because at the horizon, things have to go in, and then at infinity, things have to go out, right? So these waves, they have to decay, right? These modes, they have to decay. So this omega is complex. And if you break it into like an imaginary part and real part, then obviously you get something like this, right? There's one quasinormal mode. There is some oscillation, which is governed by the real part, which is frequency. And there's some decay, which is governed by the imaginary part, right? So this imaginary part is always negative, right? At least for the cases that we're looking at. So it is a decaying oscillation. Usually we plot the absolute value and we plot it in log scale so that it's super clear that it's decaying exponentially. Okay. Now, yeah.
What sets the phase in this case? Is there an infinite?
So the phase is set by the initial conditions of your perturbation.
Mhm.
Okay. So what do these quasi-normal frequencies look like? So these omegas, right? I said that there are only discrete allowed values due to the boundary conditions. So in the complex plane, you can plot it like this, right? This is like the 2 to 0 quasi-normal, which I will mention a lot. This is also another quasi-normal which I will mention a lot, the 2 to 1. So the first number is L, second number is M, third number is M. So these are all inside of the Lm equals 2 to harmonic, and this is the dominant harmonic because of the symmetries of our system, right? Like you have, yeah.
So why do the modes decay in this case? Like you were talking about hydrogen atom, but the modes, the hydrogen atom appear lost.
Yeah, it's like mathematically speaking, it's like the problem is non-Hermitian. Yeah. And basically the way to understand is that like at the horizon, things need to go in, and at infinity, things need to go out, right? So things are leaking away, they're dissipating. So it has to decay. Yeah.
So if you didn't have a horizon like a neutron star, say, the modes wouldn't decay in that case.
At infinity, it still has to decay, but like it still has to go away. So it would still.
Or would it decay slower?
I bet, yeah. But there'll be other modes, like there'll be like the F mode and like the usual like stellar oscillation modes. Okay. Yeah, so the Lm equals 2 to mode is usually dominant inside of like when we talk about gravitational waves for binary black hole mergers because of the symmetry, right? You think about it like there are two black holes like this, then the dominant like the symmetry is that like it's like quadrupolar, right? So the 2 to mode is dominant, and this 2 to 1 overtone frequency, we call it an overtone, and this one is a 2 to 2. It's called a second overtone, and there's the third overtone, fourth overtone, and so perhaps now you understand why we call this black hole ring down, because this is just like when you strike a bell with a hammer, right? Like you listen to a bell and you know that it is a bell because of the overtones, right? If there's only one frequency, then a violin would sound like a bell if the notes are the same, right? So it is the same for a black hole, right? You strike a black hole, then you will hear its frequencies in terms of gravitational waves. And if you can hear many of those frequencies, then you will know that what you struck was a black hole, right? So
Usually ends are denoting like number of radial nodes or something. Is this
yeah,
here as well?
Yeah. So different modes have different radial nodes. Yeah. So this quasinormal, because it is in the dominant harmonic and also it decays the slowest. Like mind you, this is the imaginary part of the frequency which governs the decay rate. So this one decays faster, this one even faster, and that one will be like even faster. So this one is the dominant one inside of the ring down. And of course, there's not only just the Lm equals 2 harmonic. There are also like 210, 330, 440. Like these are the ones I highlight are the ones that are usually most important, depending on the initial conditions of the binary. And of course, there are an infinite number of them actually, right? Okay, so what do we want to do? Basically, what we want to compute these frequencies in theory, and then we look at the ring down signals that we detected, and we compare them, right? See whether they are the same as each other. If they are consistent, then our theory is good.
And the radial nodes are inside the horizon or outside?
Outside.
You only start at L equals 2 because you're only tracking gravitational radiation, so you need something quadrupole, or is it something about or is it something about the setup that leads to the ring down that doesn't have any 0 and 1?
It's like L equals, like we need to look at L equals 2 because this is like gravitational perturbation, right? It's like spin 2 perturbation, right? If you're talking about like scalar modes, then like the L equals 1, L equals 0 will also be excited.
Like they can exist, they're just not relevant for the problem you're thinking about.
It's not relevant if we're talking about gravitational perturbations. They cannot exist.
To what extent do you kind of get nonlinearities kind of coupling between these at the maybe early stages of the ring down?
Yeah. So like one mode can couple with another mode to produce a quadratic quasinormal mode, or even like third order, fourth order. I'll talk about this later. Okay. All right. So what is the status of detection of quasinormal modes inside of the ring down? Right? Like because the goal is actually to detect multiple quasinormal modes. Because there's this black hole no hair theorem where like each black hole is only described by 2 numbers, right? So if you measure one quasinormal, that is 2 real numbers, right? So if you measure these 2 real numbers, you can infer the quasinormal modes. Like you can infer the frequencies of all of the other quasinormals, right? So if you measure 2 of these quasinormals, you can compare them and see whether they are consistent with each other. If they're not consistent, then the no-hair theorem is broken, right? So it is always the goal to detect 2 quasinormals, okay, at least. So for the first event that we ever detected, GW 150914, the famous event, we found 1 quasinormal, right, confidently. And then there are also claims of detection of multiple quasinormals, but those are not as confident.
How do you know that this is definitely a quasinormal mode rather than just some decaying signal?
That's a very good question. I'll talk about this later. Yeah. So, and yeah, as I mentioned, we want to have multiple detections. So this is studied actively, and there were some claims, and then different people claim detection of different quasinormal modes. Results don't seem to be super consistent with each other, and that is until like I think that it was last month that this new event was released by the LBK collaboration. I think Salvo mentioned this very briefly. So on top here, it's this event, like 150914, right? And you can see that it is kind of buried inside the noise. You can kind of see some oscillation. And if we're only looking at the ring down, and it is this part, right? And it is pretty noisy, right? But then this new event, like GW 250114, basically with almost exactly the same parameters as like 150914, you can see that it's much cleaner because our detectors improved a lot, right, over the 10 years, right? So this time the ring down looks much cleaner, right? And
how is this green curve computed? How is the green line computed?
The green line, it is the maximum likelihood parameter that fits the data well.
But the
The
template,
it's, yeah. You can think of it as the template, yes.
Sinusoidal is just before the merger, like minus 0.2 seconds. And then
Here?
yeah,
Like, why is it sinusoidal?
it's not very sinusoidal.
It's not very sinusoidal, yes. It's, oh, you mean, okay. This is,
Looks possible.
sure. So firstly, this is, oh, you mean this one, maybe? Like
This one's probably noisy, right?
yeah. So the green one is a whitened version of the waveform. So it is a little bit distorted. Like basically the low frequency components, because it is noisier. So when we whiten it, it's reduced. So this is not exactly what you see if your detector is without noise. Because we need to whiten the template according to the noise. That's why you see some distortions here, perhaps.
You have the version of this lower figure without the green curve.
Oh, you, they do. I think in the paper, do they? I don't think so, but I can make a plot and show you later.
but does the green curve come from theory, like BN approximation or something like that?
Yes. It's from, so it's from a waveform model. So basically we use a waveform model to fit the data, and this is the best fit. And the waveform model comes from some theory and also calibrating within our simulation.
And by the way, this event by itself was much stronger.
Yes.
Okay.
No, actually, sorry, no.
So it's just the
Like the, yes, the detector improvement, yes.
Same distance?
Distance is similar, yes. So like the SNR is stronger, but only because of the N, right? Because of the noise.
So it's noise got improved on the same.
Yes. So this is all because of us, like humans. Okay. So, okay, in this event, if you look at the abstract of this paper published in PRL, like the discovery paper for this event, it states that the post-merger data excluding the peak region are consistent with the dominant quadrupolar LM equals 2 mode of the curve black hole and its first overtone. So the 2-0 plus the 2-1 mode. Okay. So that's amazing, but how did we get here? How did we get from like a single mode detection to like not confident detections of the second mode until now we confidently see the second mode? Okay. So this actually relates to one of the main themes of my PhD thesis, and that is like the detection criteria for quasinormal modes, which relates to something like this mentioned. Yeah. So the one question that bothers me always during my PhD is what do we mean by a quasinormal mode being present inside the ringdown? What is the detection criteria? Right. So let's say let's start like a little bit naively, and we say that a mode being present means that including that mode in the ringdown fits the signal better, right? Because some modes are expected to be there, right, from theory, right? Like we can compute the quasinormal frequencies at 2-0, 2-1, 2-2, 2-3, like many of these quasinormal modes. And we can see if these modes, they fit the ringdown waveform well, right? Like, for example, I have a model with only one mode, 2-0, I fit it. And then I have a model with 2-0 and 2-1, I fit it again. And then with 3 modes, I fit it again and see if the fit, see if the fit improves, right? But of course, it's going to be improving, right? Because you're just overfitting, right? Because every time we include one mode, we know the frequency, but we don't know the amplitude and the phase, right? So we need to leave the amplitude and phase free. And those are free parameters, right? And the quasinormal modes, they are actually very, very good at overfitting. Because if I show you here, I plot the quasinormal modes like with n equals 0, so this one, and then n equals 1. So this one like decaying faster and faster and faster. And at some point you don't really see the oscillation anymore, right? Because when you're fitting, you're doing like a least squares fit. Then the early part, before it decays exponentially, it matters the most, right? This part. So basically you can fit almost anything with the early part if you include enough quasinormal modes. They just kind of cancel each other and fine tune, right? So quasinormal modes, they are very good at overfitting. So we need a better strategy. So how should we avoid overfitting? Now, a quasinormal mode, it looks like this, right? There are many numbers in a quasinormal mode. So perhaps we should try to verify whether each of these numbers are giving what we expect, right? So firstly, how about we fit the quasinormal mode without fixing the frequency and asking the fitting algorithm to return a frequency. And if the frequency matches our theoretical predictions, then perhaps it is a quasinormal mode, right? So the first question we should ask is whether the frequency itself is present. Yeah, I'll show you what I mean later. And then this amplitude and phase, this is not a function of time. The whole quasinormal mode is a function of time because of this t, but this is constant and that is constant. So are the amplitude and phase that we extract from the data or certain simulations, like are the amplitudes and phase, are they constant in time? Because if they're not constant, then it seems like it's just fine tuning at different times to fit different amplitudes.
When you say constant in time, you mean respect to when you start the fit?
Yes, yeah. I'll show you an animation to clarify later. Yeah. And finally, do we see the mode in a long enough time window and not just briefly? Because quasinormals, they decay. So whenever you're starting to fit, only the early part of the quasinormal matters, right? So if you go later and later and later for your fit, then you will see different results. So do we see consistent results over a large time window? That's the third criteria that I want to test. And I wrote a package called Jacqueline. This is not AI, by the way, this is my fiance. Like she drew this. So I wrote a package called Jacqueline to systematically do this. Okay.
You also expect the amplitudes and phases of neighboring modes to be correlated with each other. They won't be completely random.
Yes, so from NR simulations, like given some initial conditions, we know how the amplitude and phase of different modes are related. Yeah. It's a little bit difficult to compute like analytically, but we can look at NR simulations.
They should at least not be completely random.
It's
Whereas
not.
if you would just fit in noise, they would be completely random.
Sure. Yes. Exactly. Yeah. Okay, so. Yeah.
I have a question, maybe related to this one. When you model those modes, you assume that you have two black holes and they're the only ones in the universe. So the question is, do you have a similar template when you have a perturbation, or equivalently, how well do you know to model the noise?
So you mean for the quasinormal modes, like if there's something surrounding, like for example, like
a flyby, let's say.
a flyby. Okay, that one you need simulations, and then you need to look at those simulations, and those I don't think those are super yet. Like you mean like a free body thing, or
For example, yeah.
yeah that like the parameter space is just too high. Like here this parameter space is simple because it's just two black holes, right? But it's already very hard to cover the whole parameter space because of the spins and everything. If there are free things, then it's pretty expensive to do, and I don't think anyone has done like a full like NR simulation for free body things. Are there any? They haven't looked at this. But people have done few body. Sure. But for the time being, I'm only looking at like vanilla binary black hole mergers. Okay, so first question I would like to ask when I want to understand whether a quasinormal is there is whether the frequency is actually there. So I fit the waveform. This is a very simple, this is just a linearly square fit, but I do one fit with this time window, I do another one like this, and I do another one like that, do another one like that, do another one like that. And it will give different frequencies, right? And so I check whether when I change the starting time of this fit window, whether the frequency goes to the value that I expect, right? If it goes there and stays there, then okay, this quasinormal mode is there, right? And as you can see at the later time, it fits better, right? Because we're applying perturbation theory, right? With like when computing quasinormals, and perturbation theory works better at a later time because it is closer to a curved black hole. By the way, I'm fitting simulations here. So these are numerical relativity simulations. There's not real data. Okay. So everything I'm talking about here is like fitting simulation.
Can you remind what is stabilization by M?
Oh, M is so because like if your system is 10 times heavier, then the time scales are like 10 times longer, right? So when people do simulations, like they just use an arbitrary time scale that is like normalized by like this total mass m.
So instead of taking Cantu, you take a Laplace transform or something.
That's a question I've always been thinking about, but it's not that simple. At the very least, because your ring down, it starts abruptly, right? Like so, even if you want to do a Fourier transform, right, to analyze this data, it's already pretty messy, right? So the easiest way to do it is to actually just fit it directly.
The plus, you have to do it in the full complex plane, and then you have to look for simple poles.
Yes.
That's what I think.
Yeah, for theoretical calculations, they use Laplace transform.
But this stuff looks pretty smooth, and like maybe not the actual universe, but like your numerical simulation.
It looks pretty smooth, yes, but the problem is like if you're just fitting for one quasinormal, like just now, it's okay. But we want to find the subdominant quasinormals that don't show up when you look at this. Like those are like those decay very quickly, or they have like very low amplitudes. Yeah, that is the problem.
I guess more precisely, so what actually is M? Is the ADM mass of the per remnant, or is it something else?
It's the crystallographic mass of it's not of the remnant though. Wait, is it? It's total mass and remnant mass. It's pretty similar, but it's one of them here. Okay.
Probably for the initial system.
Yeah. Yeah, actually, yes, because that's the easiest to control for in your simulation. It's just the mass of the initial condition slice.
But then it's a mass is dissipated through gravitational waves, so there should not be the mass controlling the frequency.
Yeah, it's not. Yeah, there is a mapping. There's a non-trivial mapping.
Okay, so you compute the frequencies you expect with the actual.
Yes, because from the simulation they can also approximate the random mass. Okay, so sorry, I've been jumping between. Okay, so with one quasinormal, then it's pretty clean, right? It just goes there, right? When you go to a later time window. And then with two quasinormals, for example, here I can fix one of the frequencies and then put another frequency there and see where it goes, right? So at some point it seems to be flirting with this 2-to-1 frequency, right? So perhaps this is also there, but then at the very end it goes somewhere else, right? So what is happening there? Now, if we include many modes in our fit model, then we will find that a lot of modes actually exist in our simulation, right? So like 2-to-0, 2-1-0, 3-to-0, many modes. It's a very rich spectrum, right? So now we can begin to verify whether each of these modes are actually there. So this tells us that there are hints of these different modes, but then we want to use additional conditions to verify. Okay. So second condition. Is the mode amplitude constant, right? This is a constant in time, right? If I vary the fitting time window, does this give me a constant result? For one mode, the 2-to-0 mode, I fix the frequency and then now I just fit for the amplitude and still I change the starting time of the fit, right? So as you can see here, the amplitude, don't know why this happens. Sorry. As you can see here, the amplitude goes to a constant at some point, right? Like it's the amplitude extrapolated back to the peak of the merger. So this mode is pretty robustly extracted. Now, if you have two modes, 2-to-0 and 2-to-1, then you'll see that both of them are pretty constant in the middle, and then the overtone amplitude blows up. But this is expected because the overtone hit the noise floor at some point, right? And if you go later and later, it's just fitting the same noise. But because it's later, you extrapolate it back, it blows up. Yeah. So, but in the intermediate time window, both modes are pretty constant, right? So yes. When you extrapolate it back to the peak, right? So in this region where both amplitudes are constant, I trust that the mode is there, right? So in that region, the amplitude is actually a little bit lower because like the amplitude I plot there is the amplitude at the peak, right? Does that make sense? Like because it decays, right? So when the mode is actually confidently there, the amplitude is already pretty low because it decays faster. So with this procedure, I can verify whether different modes are there, and if the amplitude just varies quite a lot, then I can have like a procedure to just throw away that mode. So in the end, for all of the simulations that people have performed inside of this 3D parameter space, so this is like the ratio between the two masses. This is like the combination of the spins of the two black holes, and this is another combination. So basically, it's a 3D parameter space of binary black hole mergers with aligned or anti-aligned spins. Okay, so in this parameter space, people do a lot of simulations, and in each of those simulations, I can extract all the quasinormals that I can extract according to the criteria that I talked about just now. And then all of them, I can extract the amplitudes, and I can have a so-called hypermodel of all the amplitudes, right? And then you can use this to also test your theory, right? Because before I was mentioning how you can test the theory by comparing the theoretical frequencies with the observed frequencies, right? But now you can also compare the theoretical amplitudes, which is this, with your observed amplitudes, right? So how does this relate to the new detection of the overtone inside of GW 250114, right? So I need to say that they didn't really use my work directly, but they applied the philosophy. so yeah, make my I don't want to take too much credit. So for 250114, they found evidence of 2-to-1 mode. Like before, all of the detection claims usually they don't meet all the 4 criteria that I mentioned just now. So quasinormals, there are 4 numbers, right? Amplitude, phase, real part of frequency, imaginary part of frequencies. All 4 of these numbers that you extract from your signal, they should be consistent with the theory before you can say that it's a real quasinormal that you extract, unless you believe that GR is wrong, right? So they found evidence of 2-to-1 mode, and the amplitude, if these are the posteriors for the amplitude at different times, they are consistent with the amplitude they extract from NR simulations at the most stable time window. Right? As I showed you just now, the amplitude, it varies and then it settles down in an intermediate region and then it blows up again. Right? So the amplitude at the most stable region, the posterior is consistent. The phase is also consistent with that. The frequency of the 220 and the 221, the posteriors, are also consistent with that. So all 4 numbers are consistent. Right? So this actually meets the necessary condition for claiming that you detect a quasinormals. Whether this is a sufficient condition is another problem, but we can talk about this in private later. But anyways, this is consistent with the detection. Okay. Any question?
How are those posteriors derived? How are the posteriors obtained?
So they look at the real data, and then so basically they have a quasinormal model and they do Bayesian inference, like assuming some model for the noise, and then they get like a probability distribution for the parameters, for the frequency.
So that fitting, that doesn't include the simulation. The simulations are independent.
Yeah. Similar. No. It's independent because these are just quasinormals. So in your model, it's just A times e to the I omega 2. Yeah. And then this point is obtained by applying the same model but to the simulation.
So if your goal is, for example, testing the Nonlinear theorem, then isn't it a little bit of a circular argument? You say the frequencies, so I only accept a quasinormal mode if the frequencies match my theory, but I want to check my theory.
Okay, sure. Yeah, that's exactly why I say this might not be a sufficient condition, because if you do not assume any theory, then you should actually check whether the frequency you extracted here is self-consistent. So you should go to a later and later time window when you are trying to analyze your signal. You go to a later and later time window and see whether the frequency that you extract is consistent with the earlier time window. Yeah. Then you will know that what you extracted is robust, and then you compare with your theory. Right? So that is hard to do because you need very high SNR, right? Because your signals are decaying. Right? Okay. All right, so what's next? I'll very briefly mention because I'm a little bit out of time. So what's next? So other than those linear quasinormal frequencies, those overtones, there are also nonlinear quasinormal frequencies. They are quadratic modes. So for example, you take like one of the dominant modes and then you take another one of the dominant linear quasinormals. They can interact with each other because gravity produces more gravity, right? Gravity is nonlinear, right? They interact with each other to produce second order modes. So this is just a sum of the frequencies of linear modes because these are exponentials, right? You multiply them, the frequencies is the sum, okay? So in simulations, I actually found quadratic quasinormals, which is very exciting. And with a student still at Johns Hopkins, like Sophia Yi, we tried to quantify whether these are detectable, and most likely we'll need like next generation detectors like LISA. However, given that you see a copy of the same event every 10 years with much better noise realization, we will also try to quantify whether we can detect quadratic modes if we see like yet another improvement of this event. Something like that.
Are the amplitudes for the quadratic modes just given by some combination of the amplitudes of the two?
Yes.
Or is there some extra scatter there?
There is a little bit of extra scatter that is related to the final spin of the remnant, but it's very much universal other than the spin. Like no matter what your initial conditions are, as long as the remnant spin is the same, then you will find that it's just some square of the amplitude with some coefficient, and the coefficient is similar for different. Like when your random spin is the same, the coefficient is the same. This is also something I verified by looking at simulation.
So this is another consistency check, I guess, when you can try to fit for the two linear modes and then see if you find a quadratic mode with the expected amplitude.
Yes, exactly. But we need pretty high SNR to do that. So maybe in LISA that would be possible. So yeah, given that we will see something like this, we expect to see something like this again with better noise, then we'll try to see whether we are doing a forecast and trying to see whether we will be able to measure these quadratic quasinormals in the future. Yeah. Okay, so for the second part of my talk, I'll talk about how you can inform astrophysics with gravitational waves. Okay, so I think because I also have the Astro Coffee next week, and I think I'm running out of time. So maybe like for the higher order mode search that I've been doing with Matthias and Jay and other people, I'll talk about it in the Astro Coffee maybe. Yeah. So you can ask questions whenever you like. Okay, but before I talk about like the high mass spatial search, I'd like to talk about gravitational wave lensing, which is something that I've also been doing during my PhD. So everyone knows how gravitational lensing itself works, right? Like there's a star or some object, and then the galaxy lenses it, and then you see multiple images, right? This also happens if you have gravitational waves, right? So if you have gravitational waves, then this will happen. You have two like copies of the same thing, like two images. And because their travel path is different, so one comes first, you detect it, and then after a few days, you detect the other one, right? Maybe a few days, maybe a few weeks, or a few months. Now, what if the lens is actually very, very small? Then this time, you only see one thing. But it interacts with the lens and gets diffracted. Because when you have a wavelength that is comparable to the length scale of your lens, then it doesn't really see the lens and it gets diffracted, okay? So there will be some non-trivial frequency dependent modulation to the original waveform when you detect it, in this case, okay? And this is the case that I studied in my PhD. So if you have a model for the unlensed waveform and then you detect an unlensed wave, then you can extract the properties of the source, right? But if you have a lensed waveform and you also know how to model this lensing effects, then you can also extract the lens properties, like on top of the source properties, right? And then you can do all sorts of physics with that, right? Now, the problem is that computing this thing, you need to be able to compute it very quickly if you want to do Bayesian inference, because you need to call this like 10 to the power 7 times during your inference. And so efficient computation is required for this lensing, so-called lensing amplification factor. And it is
multiplicative, it's not a function.
It's multiplicative, yes. So it's because you can think of it as like a convolution in the time domain, and then when you Fourier transform, it becomes. I'll talk about the time domain later, actually. Okay, so what does this amplification factor look like? Let's say your lens is an NFW model lens, right? And the amplification factor looks like this. It is oscillatory, and it is very difficult to compute this in the frequency domain itself, okay? So it is actually easier to compute in the time domain, and working in the time domain also allows us to interpolate this inside of parameter space much easier, right? Because as you can see here, if I want to interpolate this thing, it's very difficult because the oscillation period inside of this frequency domain, it's varying quite a lot when we change the parameters, right? But in the time domain, it's pretty simple. Basically, it's like a non-smooth thing, because the zeroth order effect of lensing is that you have different copies of the same image superimposed with each other, right? And then you add also some diffraction effects on top of that, right? And when you want different images to be on top of each other in the time domain, it's just some delta function, right? That is separated by like some time difference with each other, right? So it's an unsmooth thing in the time domain, but it's easy to interpolate as long as I divide this into different ranges, right? And then like for different parameters, it's only the range here or the height here that changes a little bit, and I can interpolate it, right?
You're just looking at one polarization here.
This is like whatever polarization the lensing is the same. You just multiply by this amplification factor. Okay, so I wrote a code to compute a bunch of examples of this like time domain amplification, and then I interpolate it for like over the range of the parameter space, and then like I just call it very quickly and do a Fourier transform. Then I can compute like the lensed waveform, right? And then I can analyze the signal. Right? So like in the second half of my PhD, I did this, and here this is the result of analyzing a simulated lens gravitational wave signal. And as you can see, I can recover the parameters of the lens. Like for example, this kappa is a parameter of the NFW halo, and I can extract it, and I can also extract the impact parameter y, and also the mass of the lens. Right? This is only a simulated signal, so this is just to prepare for real noise detections. Right?
This is what's you know the frequency distribution within the lens.
Yes. So I need to assume some model for the distribution.
What's the number over there? I'm curious what the mass of the lens is.
This one?
Yeah.
This is
I just can't.
no. This is just this is a simulated injected signal, so I can put whatever mass, and I put 100 lens mass equals to 100.
But it depends. I mean, for you to be in this diffraction regime.
Oh yes.
So the wavelength of the gravitational wave is what we're kind
the wavelength is so basically like with like the lens mass has to be like below 10 to the 4, something like that, for diffraction effects to be very important. When you have higher masses, it's still there, but it's less important.
That's for 30 plus 30 plus.
Oh no, oh yes. 30 plus 30 for the.
What about neutron stars? Binary neutron stars.
Binary neutron stars, so
That would need to be smaller, right?
Binary neutron stars, it actually depends on the frequency range that you're sensitive inside of the detector, right? Like for binary neutron stars, like there will still be there will still be a low frequency component, right? Like the inspiral, right? So that part could also be affected by diffraction effects when you have like a lens mass on a similar scale. Yeah. So it depends on the sensitivity of the detector actually. Okay, so I did this and I'm like, okay, I press skip push and then for 5 years I don't have to look at this until I actually see an event, or maybe a poor grad student will inherit the code and then do the analysis by that, right?
What are you using for the distance of the lens?
The distance of the lens here.
Yeah.
So it's for the injection, I think if I remember correctly, this is like the source is at redshift 1 and then the lens is at redshift 0.5. But we can't really recover the position of the lens because there's some degeneracy. This MLC, all of these parameters like Y and kappa, they depend on where the lens is. So there's some degeneracy that we will not be able to resolve.
Maybe a related question, what happens if instead of one lens or one galaxy, you have in the middle several galaxies and each one of them has different parameters? You want to be able to decouple between those, right?
So this is very rare in our case because we didn't even see a lens defend by one thing yet. So it's pretty rare, but people have been trying to compute that. But the parameter space is obviously like much larger, and like basically because when we detect signals in gravitational, it's just a time series, right? So you can't really see too many things like inside of a gravitational. It's not like you have an image, right? And then you can map out many things. Anyways, so okay, I thought we'll have to wait a long time before we'll see something like this until this happened. Like GW 231123, this was released in July. And this is an extraordinary event, very extraordinary because it is a binary black hole merger with total mass that is very high. We have never seen a binary black hole merger with a mass this high. So the primary mass, like this is assuming that it's not lens, okay? Assuming that it's not lens and people do an analysis, the LVK collaboration do an analysis and they find that the primary mass is around like 120 and the secondary mass is also around like 100, 120. And no matter how you try to shift the boundaries of the upper mass gap, like the pair instability supernova mass gap, one of these masses have to lie inside of the mass gap. So we can't just explain how these black holes are formed by core collapse, okay? And another thing that is very rare and unexpected in this event is that the spins are both very high. So both of them are consistent with extremely extremely spinning black holes, right? So with like stellar evolution and then collapsing to form binaries, the natal spin just isn't high enough to explain this. And even if you have multiple mergers, like so-called hierarchical mergers of black holes to form these bigger black holes, the spin still wouldn't be consistent with a spin that is this high. Because after you merge, because after a binary black hole merger, the spin is high. But if the spin is too high, the black hole gets kicked away from your dense environment and it doesn't merge with any other things anymore, right? So it's very difficult to explain with our current understanding of how these binary black hole mergers form, right? So what if this is lens, right? What if there's some frequency dependent modulation due to the lensing effects that caused us to mistake this as a high mass and a high spin black hole? In fact, inside of the LVK paper, they also said that their preliminary analysis suggests that 2311 shows the strongest support for distorted lens signal seen so far for a point mass model. So for a point mass lens with diffraction they found that there is some support, okay? Although they suggest that there are some false alarm issues, but still this is interesting, and of course I should look at this. By the way, I think they will have a paper about this very soon, maybe in the next month.
Is there also a signal at a similar, with a small time delay that?
With a small, oh no, I don't, maybe there will be some targeted search later, but like with the vanilla search, like we didn't find anything. Yeah.
What is the average time delay that you expect for lens gravitational waves?
Good question.
Like for lens CDM halos?
Depends on the mass range. Yeah, like you have like if it's a higher mass, then time delay is higher. Lower mass, time delay is lower, and also depends on the impact parameter. So I think in principle, you will be able to see all sorts of time delays that you want to see, depending on like if you allow for a huge mass range. Yeah. However, the relationship between the magnification of different images and the time delay, like there are some constraints. There's some surface in parameter space that you have to lie on.
It's like probably like in strong lenses, right? So
Yeah.
So you know, these lens supernovae.
It's frequency dependent, right? So I wasn't like,
So
the parameters of the lensing are going to depend on the frequency of the wavelength of the wave signal that you're getting and the configuration of the lenses, right? So I just wasn't sure.
so if
Are you talking about the individual images? Right.
Yeah, is that always going to be the same for both cases?
So if you're talking about very massive halos and like very distinct images that come one after another, then the wavelength will be short compared to the length scale of the lens. Then the frequency doesn't matter.
Yeah.
And these are just magnification and also time delay. Those are the only numbers that you get. But here in principle, you get like an infinite number of degrees of freedoms because like you have your frequency range is like you can divide it infinite. Okay. So if they mention this in the paper, then of course I need to run my code on the event, right? And the preliminary results suggest that yes, this thing could be this event could be consistent with diffraction lensing. We find a very low impact parameter. It's consistent. It's actually hitting the lower bound. I can't really go below the lower bound because it's becoming difficult to compute the lensing integral. And the mass is consistent with around like 10 to the 4. Okay, so diffraction effects might still be there, but not super important. And here I look at this event with 3 different lens models, the point mass lens, this GSIS lens, so it's an isothermal sphere, but I allow the slope of the density profile to change, and also a chord isothermal sphere, where I just put a core at the center of the sphere. Right?
What's Y?
Y is the impact parameter. It's a normalized version. It's for the point mass lens, it's normalized by the Einstein radian.
But this mass is not the real mass. There is
It's-
some redshift based on this.
Yes, it's not the ethereal mass at least. Yeah, like the ethereal mass. Okay, for point mass, I assume that it's just a black hole with a ethereal mass of a certain halo. I mean, because later I'll use the halo mass function to quantify how rare these kind of events are. And for the point mass model, I just assume that every halo is a point mass with the corresponding Fourier mass. But for GSIS and CIS, the lens mass is actually 1 or 2 orders of magnitude lower than the Fourier mass. Because lens mass, it only depends on like the central region of the lens. Okay, so preliminary analysis suggests that this is consistent with very, very strong lensing because like the impact parameter is low, right? If it were not lensed, then this posterior will be consistent with very high values of impact parameter, basically no lensing, right? Okay. Now, even more excitingly, because after we include the lensing model, it will also change our inference of the source parameters, right? So for the unlensed case, we find that the masses of the binary, they are very high, right? And they lie in the mass gap, right? But with lensing, it becomes a much lower mass binary black hole. And this is because with lensing, basically it boosts, because of the magnification, it boosts the amplitude of the gravitational waves. So it actually came from further away and it gets redshifted, right? So the mass is actually lower, right? And the spins, right? The spins are actually unmeasured if we include the lensing effects, right? So now we're less confident, like if it were lensed, then we are less confident that it is a highly spinning binary, right? Okay, so do I believe that it is lensed? Well, remember, Salvo in his talk, he said, okay, from a cup of coffee to his house to his life, like what would he bet, right? I don't think I'll even bet like the coffee because this doesn't this shows that the lens model fits the waveform well, right? It fits the signal well, but we also need to quantify the prior probability, right? Do we expect the unlensed hypothesis to be rarer or the lensed hypothesis to be rarer, right? And this is what I'm doing now because both hypotheses are actually pretty rare, right? On the one hand, it's like a unlensed but high mass and high spin. This we don't know how to explain. On the other hand, it's a lensed event, and for lensing, we can compute the optical depth, and the optical depth is actually pretty low. So if I use the halo mass function and I do all the conversions between land mass and virial mass, I find that the lensing probability is pretty low. Okay, but these two these two hypotheses, we're still trying to quantify which one is rarer, but seemingly like it's within the same order of magnitude, the rarity. Okay.
How does the chi-squared for the waveform change in the lens case?
So we do chi-squared. So it's like maximum likelihood. It's within an order of magnitude.
And for how many new degrees of freedom?
For 3 more degrees of freedom. Yeah. For 3 more degrees of freedom. Yes. But it's because for the lensing case, it's like a completely different set of source parameters. So it's not like for the lensing case, I can tweak the waveform a little bit such that it fits it better. No, it's actually a completely different set of parameters. So it's completely 2 different hypotheses. Yeah. And the way to do this is actually to quantify the prior probability properly. Yeah. And even after quantifying the prior probability, seems like the 2 hypotheses, they are it's more or less a coin flip, like both are pretty likely, like equally likely. But we made some assumptions on the lens model, right? Like for example, here, this lens model could be super concentrated, and this point mass, I mean, we're just assuming that all the halos are super concentrated. So we boost the lensing probability a little bit. That's why I won't even bet the coffee. Am I out of time?
I'll give you a couple of minutes. There have been many questions.
No, but and then this is the final part, but I can talk about it in the astro copy, I guess. But these are just preliminary results. So that's why I didn't show any numbers like the base factor or anything. Yeah, but stay tuned. Yeah. Okay, so this one I'll show maybe in the astro copy, but yeah, basically I did like some tests of GR with black hole ringdown and some astrophysics with gravitational lensing, and that's all.
Okay, great talk.
So you said optical depth for this lens event is low. This is optical depth for such highly magnified event, is it? Or because
yes,
your chances of hitting such a tiny input parameter. I mean that's
yes, exactly.
So am I trying to find something which that's a percent.
Yes.
so this would be included in this calculation.
Yes. And in fact, if we see something with such a low impact parameter, we should expect to see something that has a slightly higher, right?
Absolutely.
Yeah. Yes, a lot of that. So the problem is selection effects, right? Like with high magnification, we can see it better. And also because when we're like in our search pipelines for gravitational waves, we do not include lens effects, right? So some of those won't be able to be found. Yeah. So there's some follow-up that we might want to do. Like, because if this exists, then many more should exist, right? With a higher impact parameter.
more question, now we just launch.
So spin and lensing are degenerate in the same. That's an.
So by looking at this one case, it seems to be the case.
It's always the case with, what does this look like in the waveform previous conditional?
So yeah, so like I can give you my hypothesis. Because this is all super preliminary. Like this one, for example. Like by the way, this relates to something Matthias is also doing, like because he wants to look at the waveform and try to pinpoint like which portion of the waveform gives you the high spin, right? So I think it is because of some because this peak is higher than expected. Like if a lower spin, then you won't see that these peaks are this pronounced. And for lensing, think about it, like it's like the zeroth order effect. It's like two images of the same thing shifted a little bit and superimposed to each other, right? So it also boosts like these peaks a little bit. So there is some kind of degeneracy. In fact, there's a group that has been trying to quantify this degeneracy a while ago.
Yeah. Again, we can chat at lunch. Thank you.